Hello everyone, thank you for joining me. This video is in sequence to part 1 and 2 on the quantum computers. This is called quantum computation. It says rather than store information as zeros or ones as conventional computers do, a quantum computer uses qubits, which can be a 1 or a 0 or both at the same time. This quantum superposition, along with the quantum effects of entanglement and quantum tunneling, enable quantum computers to consider and manipulate all combinations of bits simultaneously, making quantum computation powerful and fast. Okay, so quantum effects of entanglement and quantum tunneling enable quantum computers to consider and manipulate all combinations of bits simultaneously. Okay, so let's see what quantum entanglement is. Okay, quantum entanglement is a physical phenomenon that occurs when pairs or groups of particles are generated or interact in ways such that the quantum state of each particle cannot be described independently of the others, even when the particles are separated by a large distance. Instead, a quantum state must be described for the system as a whole. Measurements of physical properties such as position, momentum, spin, polarization, and polarization are performed on entangled particles and are found to be appropriately correlated. For example, if a pair of particles are generated in such a way that their total spin is known to be zero, and one particle is found to have clockwise spin on a certain axis, the spin of the other particle measured on the same axis will be found to be counterclockwise, as to be expected to their entanglement. However, this behavior gives rise to paradoxical effects. Any measurement of a property of a particle can be seen as acting on that particle by collapsing a number of superposed states, and will change the original quantum property by some unknown amount. And in this case of entangled particles, such a measurement will be on the entangled system as a whole. It thus appears that one particle of an entangled pair knows what measurement has been performed on the other, and with what outcome. Even though there is no known means for such information to be communicated between the particles, which at the time of measurement may be separated by arbitrarily large distances. Such phenomena were the subject of a 1935 paper by Albert Einstein, Boris Podolsky, and Nathan Rosen, and several papers by Erwin Schrödinger shortly thereafter, describing what came to be known as the EPR paradox. Einstein and others considered such behavior to be impossible, as it violated the local realist view of causality. Einstein referring to it as spooky action at a distance, and argued that the accepted formulation of quantum mechanics must therefore be incomplete. Later, however, the counterintuitive predictions of quantum mechanics were verified experimentally. Experiments have been performed involving measuring the polarization or spin of entangled particles in different directions, which, by producing violation of Bell's inequality, demonstrates statistically that the local realist view cannot be correct. This has been shown to occur even when the measurements are performed more quickly than light could travel between the sites of measurement. There is no light speed or slower influence that can pass between the entangled particles. Recent experiments have measured entangled particles within less than 1/100% of the travel time of light between them. According to the formalism of quantum theory, the effect of measurement happens instantly. It is not possible, however, to use this effect to transmit classical information at faster than light speeds. Quantum entanglement is an area of extremely active research by the physics community, and its effects have been demonstrated experimentally with photons, neutrons, electrons, molecules the size of buckyballs, and even small diamonds. Research is also found on the utilization of entanglement effects in communication and computation. Okay, so basically what they're saying is quantum entanglement allows information to transfer at speeds faster than light, which we first thought was impossible, but apparently it does exist. Okay, now let's see what quantum tunneling is. Okay, we just went over quantum entanglement. Let's see what quantum tunneling is. Quantum tunneling or tunneling refers to the quantum mechanical phenomenon where a particle tunnels through a barrier that it classically cannot surmount. This plays an essential role in several physical phenomena such as the nuclear fusion that occurs in main sequence stars like the Sun. It has important applications to modern devices such as the tunnel diode, quantum computing, and the scanning tunneling microscope. The effect was predicted in the early 20th century, and its acceptance as general physical phenomenon came mid-century. Tunneling is often explained using the Heisenberg uncertainty principle and that the wave-particle duality of matter. Pure quantum mechanical concepts are central to the phenomenon, so quantum tunneling is one of the notable implications of quantum mechanics. Quantum tunneling was developed from the study of radioactivity, which was discovered in 1896 by Henry Becquerel. Radioactivity was examined further by Curie. The idea that half-life and the impossibility of predicting decay was created from their work. Okay. Now, this is an article I saw on Science Daily. Basically, it's talking about quantum computer news. Okay, quantum computing advances with researchers' control of entanglement. Using laser light, a team of scientists has developed a precise continuous control technology giving 60 times more success than previous efforts in sustaining the lifetime qubits of the unit. Okay, using laser light, a team of scientists has developed a precise continuous control technology giving 60 times more success than previous efforts in sustaining the lifetime of qubits, the unit that quantum computers encode. Okay, a qubit is the unit that the quantum computers encode. In particular, the researchers have shown that they can continue to create a quantum behavior known as the entangled state, entangling more than 1 million different physical systems, a world record that was only limited in their investigation by data storage space. When the quantum computer was first imagined 30 years ago, it was revered for its potential to quickly and accurately complete practical tasks and often considered impossible for mere humans and for conventional computers. But there was one big catch. Tiny scale quantum effects fall apart too easily to be practical for reliably powering computers. Now, a team of scientists in Japan may have overcome this obstacle. Using laser light, they have developed a precise continuous control technology giving 60 times more success than previous efforts in sustaining the lifetime of qubits, the unit that quantum computers encode. In particular, the researchers have shown that they can continue to create a quantum behavior known as the entangled state, entangling more than 1 million different physical systems, a world record. The feat is important because entangled quantum particles, such as atoms, electrons, and photons, are a resource of quantum information processing created by the behaviors that emerge at the tiny quantum scale. Okay. So it basically states that atoms, electrons, and photons are the resource for information gathering used by quantum computers. Okay, harnessing them ushers in a new era of information technology. From such behaviors as superposition and entanglement, quantum particles can perform enormous calculations simultaneously. The report of their investigation appears the week in the AP Publishing. There's a problem of the lifetime of qubits for quantum information processing. We have solved the problem. We can continue to do quantum information processing for any time period we want, explained Akira Furusawa of the Department of Applied Physics, School of Engineering at the University of Tokyo, and lead researcher on the study. The most difficult aspect of this achievement was continuous phase locking between squeezed light beams, but we have solved the problem. Quantum computers are considered a next generation of computing after the integrated circuit, silicon chip-based computers that now dominate information processing technology. Current computers use long strings of zeros and ones called bits to process information. By contrast, quantum computers process information by harnessing the remarkable power of quantum mechanics that encodes zeros and ones in quantum states called qubits. Qubits configure in two unusual ways: superposition and entanglement. Brace yourself, quantum behaviors are very unusual. Einstein himself characterized entanglement as spooky action at a distance. Start with the fact that quantum systems can be in several states simultaneously, the up and down of superposition, for example. Particles also exhibit the quantum behavior of entanglement. It is a deeply intimate property between quantum particles that unites them perfectly in a shared existence, even at immense distance, in other words, spooky. And it is this spooky action, entanglement, that the University of Tokyo team discovered how to manage so it can be applied to run quantum computers. For the next steps of this promising path toward making quantum computing practical, Furusawa envisions creating 2D and 3D lattices of the entangled state. This will enable us to make topographical quantum computing, which is very robust quantum computing, he said. Okay, so for those of you who don't feel that this quantum computers have anything to do with the Mandela effect, they, to me, seem to have a great deal to do with it. As we've seen, all the technology here talks about quantum computers and why they use protons, electrons, neutrons to compute. They use atoms. They spin them backwards and forwards at the same time. Basically, they're using the fabric of time and space to do their computing. They're using the particles that we're all made of, that all existing things on this planet are made of. So just wanted to bring you all some information of what I had found